Welcome, this is Dr. Ali Mughebel, and we are continuing with the correlation functions. So let's look at some properties of the autocorrelation function for wide sense random processes, for wide sense stationary random process. Let's look at some properties of the autocorrelation function of the wide sense stationary random process. Okay, so by definition, the autocorrelation function is defined to be the expected value of x of t times a shifted version of that. That's called Rxx. If it's wide sense stationary, we can drop the time instant or variable, and we get only tau. What does this say? The autocorrelation function is a maximum at tau equal to 0. Why? Because at tau equal to 0, you get the expected value of the signal with itself. It gets the highest correlation. You get a measure of energy of the signal. So the first property, if you look at the magnitude of the correlation function, it should peak at tau equal to 0. Remember, we are dealing with wide sense stationary random processes. So if I need to get a wide sense stationary random process, always I make sure that at 0, I'm getting the peak, I'm getting the maximum. It can be equal, but it cannot be maximum outside. So we have less than or equal. The second property, important property for autocorrelation, is that comparing the autocorrelation at tau and minus tau, you get equality. It makes a lot of sense because these are interchangeable. I can compare today with yesterday or yesterday with today. I should get the same answer. So R of minus t, adding 1 day or subtracting 1 day in comparison should not change the fact. The third property, so it always have to be symmetric around the 0. The third property is the energy expected value of x squared is, I can get the expected value of x squared by evaluating the autocorrelation at 0. This makes sense because if you let this tau equal to 0 in the following expression, you get expected value of x squared. So there are lots of things to say from the correlation function. If the signal is stationary and ergodic with no periodic component, we can also conclude that the limit of the correlation as tau goes to infinity will approximate or will approach x bar squared. These are two different quantities, huh? They are not the same. So we have here the expected value of x squared, and here the expected value of x, and then we have the square. So we can tell what the mean is if the signal has no periodic, if the random process has no periodic component, stationary or ergodic, then you can find the mean by taking the square root of the function of the correlation as it goes to infinity. So that's a cool property. If the process is stationary but has some periodic components, so it repeats itself like we have here. So in that case, we can say that the correlation will have the same function or period as the original random process. Let's look at an example where we use these properties. Given the autocorrelation function for a wide sense stationary process, find the variance of x. Now remember that from the correlation function I can find the mean, I can find the expected value of x squared. To find the mean, we'll look at as tau goes to infinity of this, we get 25, which means that the mean equal to plus or minus 5. Plus or minus 5. Remember that if the process is ergodic and stationary, then we can take this limit. So now we also can find the expected value of x squared by evaluating Rx at tau equal to 0. So Rxx at tau equal to 0, it should equal to 29. What's this 29? It's equal to the expected value of x squared. So now if you want the variance, it's equal to 29 minus the square of the mean, which is minus 25. We get the 4. So here we're saying that the expected value of x squared is the correlation at tau equal to 0, and this gives you the mean squared. 29 minus 25 give you 4. So we also can find the variance from the correlation. So the correlation function can give you the energy, can give you the expected value of the moment, second central moment, 0, of course under some certain conditions. Here is how it looks for this specific example. I use MATLAB to generate this sketch. And remember, this is a valid autocorrelation function, so it peaks at 0. It is also symmetric around the 0, so it's a valid correlation function. The second example here states that find the autocorrelation between two functions. Find the autocorrelation of y, given that x is a White-Sense stationary with the autocorrelation given. We also are given the relation between y and x, y equal to x times cosine, where x of t and theta are independent. This condition will prove to be very handy because independence allows you to split the PDF. Omega naught is constant with omega naught is constant, while theta has a uniform distribution between minus pi and plus pi. Okay, so what's required in the question? Find the autocorrelation of y, which means the expected value of y times a shifted version of it. So we have the expression here. We'll substitute for the expression. The first part comes, the blue part comes from this term, and the other term comes from the shifted version. So we are adding t plus tau. Now let's try to simplify things. Cosine times cosine, and we know that theta and x are independent, so we can separate the expectation. That's a very cool identity or property. Without it, we cannot go to the next step. We're separating things here. We know that the first expression is the correlation of x. The second expression is, we can find the second expression here by multiplying cosine using the properties, cosine sum, cosine the difference. We have still the time variable here. And now we can find the expectation. We got the expectation of this term is equal to 0. And the expected value of cosine omega naught tau. Remember that the random variable here is theta inside the expectation. So if you average out theta from minus pi to plus pi, the first expression becomes 0. And the second one for the cosine, of course, there is no randomness here, so it goes outside the expectation cosine. What we are saying here that the original signal was multiplied by cosine to get y, and also it turns out that the correlation would be the original correlation multiplied by cosine, but there is a scaling of half. So now we are able to maneuver and play with some cosine with correlation relations. What you see here on the right hand side is how we generate y from x, and then we have the correlation of x scaled by half, and then once you multiply by cosine, it means you're going to fill the envelope with the required function. So this is the new correlation. Okay, thank you. If you look at the cross-correlation function and its properties, we now look at Rxy, which equal to expected value of x times y. When we say cross-correlation, it means that we are dealing with two random variables, nothing much. So the same concept we had before. If x and y are jointly White-Sense stationary, we may write that we may write r of tau in the following notation as function of tau only. There is no t. If it's not White-Sense stationary, we have to keep the time index inside. And if x and y are orthogonal, it means the cross correlation is going to give you 0. If x and y are independent, we can conclude that they are uncorrelated. Also, we can write the expectation, we can separate the expectation as multiple because they are independent. The probabilities will be independent. If in addition to being independent, they are at least White-Sense stationary, then the time dependence will also drop out, because if it's White-Sense stationary, we can remove the time dependence here because it's going to be second order stationary, and we get x bar times y bar. We get the average times the average. Some properties of the cross-correlation function. The cross-correlation function, the relation between, remember that Rxy is different than Ryx, because now the order makes sense, so because we have two different quantities. So now just make sure that if you flip the sign of minus t, they become equal, so Rxy at minus tau equal to Ryx at tau. The cross correlation magnitude is always less than or equal to the geometric mean at 0, which means if you multiply the two quantities, the two the autocorrelation functions by each other at 0, then you always get your cross correlation is always going to be less than this quantity. This is always less than the geometric mean. Geometric mean means you multiply and you take the square root. We also show that it's less than or equal to the arithmetic mean, which means you sum and then you divide by half. This is the arithmetic mean, that's the geometric mean. We know that the geometric mean is tighter. So this quantity is always in general less than this quantity. The green is less than the blue, so this is more dominant, the second. The third one is just automatic. So we can say that this quantity is always less than the arithmetic mean, and that's a fact. So let's conclude with this example. Suppose we observe a process y of t, which consists of a desired signal, the green signal, plus noise, the blue signal here. Find the cross correlation between the observed signal and the desired signal, assuming that x of t and n of t are independent random variables. So find the cross correlation between the observed signal at the output and the desired signal, which is x. So we need to find Rxy. We need to find Rxy. I'm going now next to replace y with its equivalent, which is x plus n, because the output is made of x plus noise. Now we can open the bracket and reorganize things. Because they are independent, I can separate, because they are independent, we will be able to separate the two expressions here into these two. To go from here to here, we invoke the independence relation. The first expression is nothing but the correlation at the input. Now, the second expression, we get the mean of the input and the mean of the noise. So the cross correlation equal to the input correlation plus the mean of the input and the mean of the noise signal. So if one of these is equal to 0, then we get the cross correlation equal to the input. Now let's look at the correlation function in the following example. The example states that we have two random processes, x and y. Those random variables are shown here. We have x and y. They are related by the following. We are told that if a and b are uncorrelated, zero mean random variables. So a and b are zero mean random variables with the same variance. Then show that x and y are wide sense stationary and jointly wide sense stationary. So the first part, we need to show that they are individually wide sense stationary, and then we'll extend this to show that they are jointly wide sense stationary. So let's see what we have. We are told that expected value of A equal to the expected value of B equal to 0. That's the stated here very well, that they are zero mean. Then we are also told that the expected value of the product equal to 0. They are zero mean and they are uncorrelated, so we get the correlation equal to 0 here. Now we are told also that they have the same variance, so I would just call this sigma squared. I'll be calling this sigma squared. Okay, so now we are defining y and x in terms of a and b. To prove it's wide sense stationary, I just need to find that the mean is constant, and then we look at the correlation. So we look at the expected value of this guy here, which is the expected value of the right hand side. We'll do it together here. So I'm just replacing x with its equivalent. Now we know that cosine and sine are not random, so they go outside the expectation. And of course, the expected value of a and b, they are both 0, so it ends up being 0. We can do the correlation function, where we multiply the expression here with a shifted version with tau. So I'm going to have two terms of him here, and then other two terms where we add t plus tau. If you multiply them, we get 4 different terms. So we get a squared times cosine cosine times sine, sine times cosine, and then sine times sine. One term had t and the other has a t plus tau, so that we execute the expression for the correlation. Now let's try to simplify things here. They could look very simple because we know the expected value of a squared, b squared, and we know all that a times b would give you 0. So all these expressions, we get they cancel out, and we get the remaining a squared and b squared. But expected value of a squared and b squared is the same. It's the variance. So we got this expression. Cosine times cosine plus sine times sine, that would be cosine. We can simplify this thing by looking at the properties we had. Cosine sum or cosine difference. It will be the cosine the difference, and we get cosine omega naught t. What's important here is that the time function, the time variable, disappeared. So a constant mean and correlation that's not function of time results in wide sense stationary x. We have proven x. We will do the same for y. We can do the same for y. I will leave this for you to show that y is also wide sense stationary. Now, to show that they are jointly wide sense stationary, we need Rxy, which is multiplying x by a shifted version of y. I'm writing the expression here in full, the expected value of x, and here is the shifted version of y. The details here are given in the definition of the function. If we open the bracket here, we get again 4 terms. Once more, we know the term that is going to cancel out to 0. And then the other term will be sine times cosine minus sine times sine. Using our trigonometry, we can see that this is equal to minus sine. So again, we can show that this is jointly wide sense stationary because Rxy, or the cross correlation, turns out to be not function of time because there is no t here. The variable t disappeared from the expression, cancelled out. If it remains, if it persists, then we can say it is not wide sense stationary. It's not jointly wide sense stationary. In our case, luckily it disappeared, and then we have jointly wide sense stationary. So the conclusion to this problem, x and t are jointly wide sense stationary. We can also extend the concept we learned for sequences, so correlation functions for random sequences. A random sequence is nothing but a discrete time random process. So we can write the samples here. We can write the samples here as n multiples of the sampling time ts. Or we can use square bracket and we write the index number. So we have the first sample, second, fourth, and so on. We can define the mean of x, the correlation. Okay, and usually we write n plus k rather than using t plus tau and so on. So the expression is usually the index n plus k. We multiply them and find the functions. We also define the covariance, the autocovariance. We had the autocorrelation, the autocovariance. We can define also the cross-correlation and cross-covariance. In covariances, we subtract the mean in all cases, and otherwise it becomes very similar to the correlation. We can relate them to each other by saying the covariance, the cross-covariance, equal to the cross-correlation minus the multiplication of the individual means, of the two means. Fantastic. So there's nothing new in this slide other than extending the work of random processes to sequences and replacing t and tau with n and k. You need to get familiar with this. So let's leave you with the following exercise. It says, in class practice, we would like to show that given that x is a random sequence, IID sequence, which means independent, identically distributed Gaussian random variable, fantastic, with 0 mean and variance is given sigma squared, and let yn be the average of 2 consecutive values of xn. So y is defined to be the average of 2 consecutive values of n. Yn equal to xn plus n minus 1, the previous value, and we divide by 2. That's the average. So find the mean of y. And to find the mean of y, again, this is not terribly difficult. We can have the expectation. Sorry, we can have the expectation. I get the right pen. So we can have the expected value of yn, which is the expected value of the right hand side, which is again going to be 0 as expected. Find the covariance of ij, again the covariance of y, which means you need the autocovariance. You need to find the expected value of y evaluated at I. Again, then you have to find multiplied by y evaluated at j. So the index is going to change here. Oh, you need also to subtract the mean. So you need to subtract the mean. So this is going to be, but the mean is 0 here, so we have no problem. So it's going to continue the same way. What is the distribution of the random variable yn? Is it stationary or not? Would like you to test this with MATLAB. You can share your answer, your discussion below. So basically you can generate random variable. You can generate the samples using Gaussian rand_n. And then you can generate another sequence. Let's call this x1, x2. It's a shifted version. And then you add them up together to get y. And then from y you can get the histogram or the PDF or the covariance or the mean, whatever you want. So I think it's good practice here to use this over MATLAB.